Good afternoon. My name is Aaron Sutton. I'm a graduate student with the Levy Lab at the University of Pittsburgh. And today I'm going to give a talk on behalf of my coworker Lu Chen on over 100 terahertz bandwidth selective difference frequency generation at LaO3 nanoscale junctions. Before I begin, I would like to thank my coworkers in the Levy Lab, our collaborators in Wisconsin who grow our samples, and also the generous funding agencies who have made this work possible. So let's begin. One of our goals in the Levy Lab is the development and use of a nanoscale terahertz spectroscopy platform so that way we can interrogate single molecules or nanoparticles with an unprecedented broadband bandwidth. Electromagnetic waves at terahertz frequencies allow resonant interactions with matter through various low-energy excitations to reveal crucial information about the materials we study. However, the rather large wavelength of terahertz radiation leads to a limited resolution spatially when imaging single nanoscale objects. Though many techniques have been developed to try to overcome this wavelength limit, many of them are limited in bandwidth or in other areas. So today I'm going to talk about how we overcome these limitations with the LaO3 heterostructure. So this heterostructure consists of two insulating complex oxides, and the interface between the two is rich with interesting physics. But what's most important to note here is the thickness-dependent metal-insulator transition. When we have fewer than 3 unit cells of LaO on STO, the interface is insulating. When we have greater than 3 unit cells, the interface becomes conducting, and a two-dimensional electron system forms. When we have exactly 3 unit cells, we're able to reversibly switch the conductivity of the interface by, say, applying a backgate to the sample and changing the polarity of the voltage that's applied. Our group has developed a method to locally modulate this metal-insulator transition. First, by conductive AFM lithography, or CAFM lithography. We first grow thin films of LaO on top of STO at the critical thickness, and we then define contacts to the interface. We then bring a conductive AFM tip into contact with the LaO. When we apply a positive voltage to this AFM tip, we deposit protons on the surface, and these in turn attract electrons to the interface, locally modulating this metal-insulator transition. When we apply a negative voltage to this tip, we're able to effectively erase the nanostructures we wrote by removing the protons that we deposited. This method is reconfigurable and reversible, and using it we can define structures as small as 2 nanometers. So that leads us to think of this system as analogous to an Etch-a-Sketch, but at the nanometer scale. Of particular relevance to this work is the nanojunction pattern. This is a simple 4-terminal device in which we draw a nanowire from a source to a drain electrode, and we create a 10 nanometer insulating gap in the middle. We also have connections to voltage sensing electrodes. We apply a DC bias from source to drain and measure the photovoltage that's generated as when ultrafast pulses hit this nanojunction. Now, how exactly does this device generate terahertz radiation? We believe it's due to the third-order nonlinear process in strontium titanate. So we have a DC bias across the junction that's highly confined in space but constant in time, and we have 2 optical fields that are highly confined in time to femtoseconds, and then we have this very large third-order nonlinearity. Multiplied together, we get this very strong nonlinear polarization that's highly confined in both space and in time. In the experiment I'm going to show, we use a sub-7 femtosecond TAS sapphire oscillator with a greater than 100 terahertz bandwidth, and we also use a 4F pulse shaper in reflection mode. This pulse shaper has a spatial light modulator, which allows us to independently address each wavelength of our broad spectrum and control both the amplitude and phase. And we're focusing on amplitude control in this talk. Here's a schematic of our experimental setup. So ultrafast pulses leave our TAS sapphire oscillator and enter our pulse shaper. Then the pulses enter our compact Michelson interferometer. We have an ultrafast 50-50 beam splitter in this interferometer, and the reflected beam goes through an optical delay line that's composed of a mirror attached to a piezo stage. The 2 beams are recombined at the same beam splitter and focused onto with a 100x objective onto the nanojunction. We then measure the photovoltage as a function of time delay between these 2 pulses. So revisiting our equation for the third order nonlinear polarization, we now have the ability with our pole shaper to ask over what frequency range, delta omega, which is the difference between the two input frequencies, can we create this difference frequency? So what is the bandwidth of our nonlinear response? Now you know the bandwidth of our terahertz generation. So let's see. Here's an example of a spectrometer image of our broadband spectrum in the red curve. And the green curve is the suppressed spectrum, so we use our pole shaper to block all of the output wavelengths. And then we individually choose two wavelengths to maximize. So here we see on the left some example time domain signals from when we have these two input frequencies. What you see in these time domain signals is both the beat pattern from the linear response at the junction, but also an asymmetry in the y-axis, and this is due to the nonlinear response. When we take the power spectra of these time domain signals, we see in the linear response range our input frequencies that go from about 330 to 440 terahertz. When we look at the difference frequency range from 0 to 100 terahertz, we see a difference frequency is generated from about 1 to over 100 terahertz. As one example, we're going to focus on this 20 terahertz difference frequency here. Just a little plug here. This achievement was the subject of a recent publication in Light Science and Applications, if you want to read more. But in order to model our results and define which components really contribute to this response, we approximate the shape of the input pulse by a Gaussian, where Tp is the temporal width of the pulse and omega c is the center wavelength. The change in the polarization of the STO is, as I showed before, so we have our linear response and then three third-order nonlinear terms. We have an optical field that is composed of pulses at time t and t minus the time delay tau at frequencies omega 1 and omega 2 that we choose as our pulse shaper. So after much calculation, our simulated photovoltage takes the following form. In the green box, you see the linear response of the two selected frequencies, which is the beat pattern that occurs. And then in the blue box, you see the frequency mixing through the third order nonlinear effect. So this is the contribution that gives us our difference frequency. In the red box, you see the induced linear and third order nonlinear photoconductive response. And this is due to the very small non-vanishing background of the pulse that remains after our pulse shaping. So let's check the agreement between this theoretical model and our experimental data. So this yellow curve here is our 20 terahertz difference frequency experiment, and our black curve is the 20 terahertz simulation. And they seem to match pretty well. So the simulation, it contains both this beat pattern and this asymmetry in the y-axis, which is what we were hoping for. When we zoom in around time delay 0, we see a very good agreement between the experiment and the model. There's a slight discrepancy here, the node around 20 femtosecond time delay, and that's due to the slight misalignment of the two pulses in our Michelson interferometer. I want to briefly just mention one application that we have done in the past that hints at future work, and that is with gold plasmonic nanorods. So we can drop cast nanomaterials, such as these nanorods, on top of the LaO, and then use our AFM to locate single nanostructures. And then we can write a custom 4-terminal terahertz generator around these devices. Now, in this experiment, we took polarization-dependent terahertz time domain signals, and we showed that the terahertz response of the nanojunction couples to the plasmonic response of the gold nanorod and shows this polarization dependence. So this shows promise for the measuring of terahertz and plasmonic properties of nanoscale objects with unprecedented resolution and bandwidth. So to summarize, the LaO-STO heterojunction interface provides a novel platform for nanoscale terahertz generation and detection. Pulse shaping has enabled us to characterize this response to an over 100 terahertz range, and it's also continuously tunable and narrowband if we want it to be. And this technology enables ultra-broadband terahertz spectroscopy at the single molecular level. So we have looked at single gold plasmonic nanorods in the past, in the future, and currently we're studying graphene nanoribbons, single quantum dots, and more. And with that, I would like to thank you for your time. When you change that last slide.